Hey, this is Steven from LegitTechTutorials, and I'd like to welcome you guys back to my product development series. This is one of my my first seasons that I came up with, and that I started on. Actually, I think it's my very first season that I started on LegitTechTutorials for my product development series. So I'm still working on this project very slowly, finishing it up from the Kickstarter about a year and 2 months ago or so. So now we have been getting more access to the 3D printer that's been down a lot at Tech Shop. Now it's been doing some decent prints. So basically we're going to be talking about setting up the last of the code to get that guy to work. All the rest of it was just standard development for the, and of course this is for the dimensional control and also the automatic spooler system. And from the last time that I did a video on this, which was probably like 3 months ago, a lot has changed on those models to get them to be where they are now. And I'm not really going to get into what I changed, because I can't even remember what I changed. So, but that's all part of development. These videos are just like, getting you up to a point, and then generally there's a lot of other stuff that happens after, just kind of tweaking stuff around and getting that to work. So what I'm going to do is start working on the code and start to integrate the HX711 up amp for the amp, for the voltage amp, for the strain gauges. That will be on the dimensional controller, and then also set up the code for the driver, the motor for the spooler, and maybe a Hall effect sensor. But mainly set up the code for the driver, the spooler, set up the HX711 strain gauge or load cell amp, and maybe a Hall effect sensor, and then I need to work on the code that basically does the algorithm that will, as I was originally thinking, it would be speed up and slow down the motor. But the issue with that is I'm going to have some sort of buffered input, so that basically when the motor will speed up its how fast it's spooling, if it speeds up very quickly, what you'll have like this bounce, right? So if this, let's just say that this line here, this middle section, is where you want to is your 1.75 millimeter or 3 millimeter filament. If you're under, or if you're oversized and you speed up very quickly, like let's just say that this was a graph, right? And so you're here, you're at 1.85, and then you speed up very quickly, and boom, now you're at low, and you speed up, and then you slow down, boom. So it's just kind of like this in and out. So one of the things to do with that is that you could buffer it to where it goes very, very, very slowly into the lower speed, but we don't have very much control with that, because again we're using PWM, and PWM on the Arduino Megas only have 255 points of precision, and sometimes when you go in between those points you don't even notice a difference. So what I'm thinking that I'm going to do instead is just use the dual H bridge, which has two outputs. One of them is to the motor that's driving it. The second one is to the spooler motor. This is, instead of doing PWM to the motor to control the thickness of the filament, what I'll do instead is control the temperature of the extruder. So that way, because when you control the temperature, again, everything's made out of steel pipe. So when you control the temperature, what you'll have is a built-in buffer where it takes a while for that change to articulate through, right? So you'll drop the temperature down gradually, like 2 degrees or so per minute or whatever, and then around that it should be able to get the Oh, also another thing I forgot I need to write code for is also the servo that winds it. I also need to do that. So yeah. So start out with it at your standard target temperature, and then if the filament is too big, increase the temperature, but yet keep the current to the motor full on. And then thus, when you increase the temperature, it should decrease the resistance against the motor, and then it would spin faster, and also it will allow the filament to stretch more, to have more of a hot zone where it will want to stretch a little more. And then if it's too small, it lowers the temperature, and then the motor has more resistance, and thus you get bigger filament. And with that, you're basically always maxed out on the motor to get your the most filament that you can get out on the spooler. So you're at the fastest speed possible for your filament to get rolled onto a spool. So you're filling up the spool as fast as possible. So let's go over a little bit of what this code looks like and give myself a refresher. I have not looked at this code in a long time. So here's a software SPI instead of hardware SPI, and you see define software SPI. And then I have 5 different files. The config file, there's nothing in there, but we have the course cal, and then this is all the boxes for. So I have a separate class for each of the screens on the TFT touchscreen. This one here is the main page, right? We have the DT, DC, TT. So diameter target, diameter current, temperature target, temperature current, all on the front page. Actually, no, this can't be the front page, because also on the front page we have. Oh no, that's in the other page. That's in the calibration page. So yeah, this is the main page here, and all the controls for the main page. Then we have fine calibration, DT, DC, extruder, heater. Oh, sorry, this is the main page. So this is the other page. But where's the This can't be the newest version I have. This one looks more recent. Yeah, so this one's got the AA. I don't know if the other one didn't have an AA. So that's an older version. So yeah, diameter target, analog amplifier. This is for calibrating the analog amplifier. Temperature target, temperature current. All the boxes on the screen that you press to go up and down. We have a green and then a red, and then this is for the to go up and down on the DT, and then here is a green and red to go up and down. The AA is green and the red to go up and down on the temperature target, and then a green and the red to do something else. This is right here, DT up and down, TT up and down, AA calibration up and down, and then here the yellow is to go to the calibration page. And here are some different things to control when. Here is like setting the EEPROM, so saving what your temperature target and what your temperature target is. So if you turn off your system and turn it back on, it will remember what your temperature target was. So writing different stuff to the EEPROM, and then here are all the these are all the plus and minuses. This is the controller. So these are the images, and then these are the controllers that are on top of the image. And I wrote a little class to do that. Then for fine calibration, so that's basically all that is just changing. This is updating the touchscreen, updating the touchscreen with the new values, right? So when you increase it, displays the new values. And then this one again is writing and reading. Well, this one's mainly writing your new temperature target. All right, fine calibration is the second page after you hit the configure button. This is basically a configure page, but I have never got around to change the fine cali up there, and you see a status page draw. Even though this is setup page draw, this is status page, which is the main screen. So this is where you turn on and off the extruder, on and off the heater, and then you hit the configure button to go to the course calibration. And then here are the images for that, and here is the updating the touchscreen when you hit one of the buttons, etc., etc. And then here's my pins page. This is where all of our pins are attached to. We're using A1, other shieldable yellow pins, A3. This is basically for, this right here is for the touchscreen. This is also for the touchscreen. The controller on the touchscreen, right, is the SAM 3X8E. And this is the mapping for the coordinate system, the Cartesian coordinate system on the touchscreen. Here's some more, the rest of the pins that are attached to the touchscreen. And the reset pin for the touchscreen, and then our thermocouple amp, our analog amp goes to A15. And then here are some of the, I don't know why that's up there. And I define it twice, so let's get rid of this. That doesn't need to be defined twice. Okay, then we have the standard colors that we're using in the touchscreen in different hex values. Yeah, 16-bit, which is hex. This is the pin motor 1 is 35, and PWM starts there. So let's make pound define. We don't need to do a space. Well, let's go over this before we start defining pins. But this is where we're going to start. We're going to start defining pins, and then we're going to start pulling stuff into here from libraries and stuff. So let's do pound define, and of course this was already pre-written, right? This was before I started the series, before I decided that I wanted to do a series like this, and before I started the spooler series. So this is just to run the multi-shooter without any of these extra expansion modules. So now we're going to add all the code needed for the extra expansion modules. So let's make this 37. So it needs to be past 35 to be PWM. So 37 should work, and also doesn't conflict with anything else. You see here that I also have a little comment thing that talks about some of the stuff that we use. Pin to change the motor that attaches to the mechanical relay. I'm not using the mechanical relay anymore. So that's why I use 34, 36. These are both to change the motor. Now I'm going to do pound define, and that's to change the direction INI motor to, and let's make this 38. Pound define IN2 motor 2. This is 39. And now basically what these guys do is the dual H bridge has a 2-pin control of the direction. Now I think if it's like you turn both of them off or whatever, you disable the motor. If one's high and the other one's low, it goes one direction, and then if you flip it, the other one's high, the other one's low, and it goes the other direction. So you can constantly change the direction. We don't really need that per se for our motor drive, but we're going to have it anyways because there's just a few extra jumper wires. Alright, Then we have our special stuff here, which is 33 for the SSR1, the SSR relay that manipulates the heater, and then this one's going to be so that handles this, that handles the extrusion. I mean the spooler motor, and then we need the no, excuse me. And then we need the HX711, which I believe was SPI 3-pin. HX711 load cell amp. So pound define. This is going to be hub. We'll just go with something like this for now. So analog to digital converter, so I think it's using tare function, blah 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 blah, how to calibrate your stick and scale, how to use, readme. Oh, it says here, move pins out. Okay, so what is a pin? Oh yeah, the gain. Oh yeah, so it just uses 2 pins. Oh yeah, and they're both analog. I remember now. It's been a while since I looked at that. This is going to be 2 analog pins. So basically we're going to be coming down from that. So we're going to say that this is, what are the 2? Something like this. Right. So this is HX711 dot D out. We'll say D out. And then this would be like A14. No, this doesn't need a closing on it. You see, none of these need semicolon to close the define. And then pound, HX711. Next one is SCK, and then this is going to be A13. And then there you go. Those are my pins that I need. So what we'll do is we'll go into MOS. So this is where all the motor and stuff is controlled. And then here is the, this is what controls the, man, this is really messy. I looked at this in a long time. Okay, this one go. Okay, so this is my main loop here. And basically what it does is it goes into here and sees that if you do this pressure thing, then output this pressure. Basically it maps the places that you press, where it gets it from the analog places. So it maps it from an analog to a digital sort of layout, to a Cartesian layout. And depending on your, I'm going to have to change that because these are for the international units, and the international units are going to have different TFT touchscreens, because I could not get the same TFT touchscreens. And when I mess with these TFT touchscreens, they're flipped. So this right here, the way I have this set up is, you see the max is before the min, and then here the min Y is before the max. So because of that change, it causes the layout on the screen to flip. So each of the TFTs, depending on which driver ICs they have, will cause the layout of the screen, the coordinate system on the screen, to be different. So for example, if you imagine your phone, and you have a button, let's just say you have a button, let's just say that this was your box. And you have a button over here that is set similar to how we have it, you know, down here in my touch box control. So if you have a button up here at the top left, sometimes when you set that up and it's not flipped correctly, the button up here is activated by pressing down here at the bottom right corner, right? Bottom right corner actually is top left corner. And then sometimes you're like, okay, well that's flipped, so you flip the getaway, and now this button is actuated if you press over your top right corner. And you say, okay, well then I need to flip the symmetry of the screen again, and then now you're finally there. So when I plug this other one in, instead of hitting here to touch the button like it does now correctly, now I have to touch over here to get the button. So I basically have to change how that's laid out on here. So the big issue with that, so you're gonna have to have two code sources. One where the internationals could have that on their touchscreen, the different touchscreens, because those are the main guys to have it. And then the second is anybody that's bought the spooler after that uses the old touchscreens. Now I'm going to have two different styles. And also two different pieces down here. And also whenever I update from now on, from this, any sort of new firmware or whatever, I'm going to have to change that. I'm going to have two versions for the people that have the different touchscreens. And then here, minimum pressure, the standard box size, diameter target starting out, blah 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 blah. Here's the touch box control, touch box method. Probably put some spaces in here, and then here's the motor control method. Here's the heater control method. You see the heater control is pretty big. Let's tab this over. And then basically what we're going to have is we're going to have a void read HX711, and then this is going to calculate read filament diameter, and then this is basically going to set the filament diameter up here. And let's go ahead and take a look at this, and then figure out what we need to import. I might even have, I might even have a example in here. Do I? It's for Mac. Oh, there we go. I don't know where this is from. This could be from these same guys. I think these are from different people. It's gonna throw an error here. Alright, disregard that for right now. Let's go ahead and see if we could open up that setup. I don't think that's the same one. But it does have those two. Okay, so that's similar. So yeah, here you got to calibrate the weight. So I'm going to have something like that on the touchscreen where you calibrate the weight, just like the analog amp for the heater. And then here you tear, resets the scale 0, 0. This value is data by caliber. No, wait. See the readme. So here, print a raw reading scale.read. After setting up the scale, print the average of 20 readings from the ADC. So we're going to use something like that. So let's go in here, go down to read filament, and then this is going to be tear. And then what we're going to have is in the setup. Where's my setup? Down here somewhere. So here's my setup. In my setup, basically what I'm going to do is I'm going to do the same thing here. EEPROM read 3. So this is going to be, I'm going to say FT, filament tear. Equals 0. And old FT tear is equal to 0. Oops. Okay, so basically let's just assume, so that's going to read that. Scale.read average. And then this, we're going to need to do some sort of and this is going to be like int filament temp. So this is filament TMP. Let's just do filament TMP is equal to 0. So basically what it's going to do is going to read the temporary filament size out of 20 different out of 20 different readings, or maybe we'll do even more. It depends on how many readings per second we could do. Oh, this is a scale, so we actually want this, not the other one. But yeah, let's also do the same thing with that. Let's do 20. So here we're going to go down here to the bottom again, and where it says setup right here, this is going to be this. This, and then this is going to be filament TMP equals scale value. And then basically what we're going to do is we need to calculate the filament diameter, which is my variable for my filament. Filament target, or diameter target, or diameter current. So DC is equal to, and I don't have ODC, do I? Oh, I do. So this is my automatic control algorithm, so that's what I'm going to go into here in a second when we get down to that point. So diameter current is equal to two things. It's equal to Hooke's law, which is F equals Kx. So K is the spring constant, and X is the diameter of the filament. So basically what we need to do is we need to also have a spring constant. So here, this is also going to have int spring constant equals 0, and old spring constant is equal to 0. So we're also going to have interfaces for each of these. Variable for the filament spring constant. So here DC is basically equals to spring is equal to F. So force is equal to Kx, right? So K is equal to so I should probably do SK, spring constant. So basically you're dividing the K over, so the force FTMP divided by the K spring constant is equal to diameter current. So that way, with the spring constant, you'll be able to get the diameter, and basically how you get the spring constant is you put a known good diameter filament inside of the in between the rollers, and then read the and then basically read the correct force. I mean, technically here everything is linear, so kind of all we need to do really is read the force and then set the force, approach the force each and every time, because there's no weird sort of it's all linear. It's all a linear equation. You know, kx. There's no squared or no 1 over x or no square root or anything like that. So all this stuff is, or no ln, natural log. So all this stuff is linear. So one of the things that you can do to get around the spring constant, because that's just another thing to set that you don't really need. I mean, well, you could have it to guess what your current filament size is. One of the things I was thinking was to have it to where you just set it, you put in the filament and have it set that on the screen. You hit a button and it sets that as 1.75 force size. So basically what it'll do is the machine will try to hit that force size over time. We'll try to get as close to that force size as possible. But you can't really, with that, you can't really display to the user a good estimate of what the current diameter is. But another thing that you could do also is you could set 2 known points, right? You could set the force open with no filament, the force with no filament in it, the force with filament in it, and then it knows both sides of the filaments, so it could, it could knock that down to 0, so you have just the force there. And then you could put K in there, and then you have KX, and then basically solve for K, right? By having no filament in there, and then filament in there, and knowing the size of the filament, which is basically X, right? X is the diameter of the filament. And then you can solve for the spring constant. So all you would do is it would be like a little button where you don't set the spring constant, but you'll have a little button on the touch screen where you press it to capture its with no filament in it, and then it says, capture again with filament in it. And you put the filament in, and you press the button again, and they'll capture that force, and then it will basically calculate for the spring constant, and then from there on out it'll be able to calculate what the diameter of the filament is, and then display that on your main status screen as your diameter current and your what diameter target you're trying to go for. And then maybe off the main screen we'll delete diameter target, because that doesn't really change, so you just have diameter current, and then at the very bottom you'll have the calibration button. Alright, so that's basically it for this video. We've kind of started here and explained what we're going to do, and we still have quite a bit to do, and we'll continue on. This has been Steven from LegitTechTutorials. I thank you guys for watching. If you like this video, please subscribe for more videos like it in this series and other series as well. See you guys next video. Thanks for watching. Take it easy. Peace.